So hello to everybody. Now let us start with the last topics of the course, which is differential equations. So the first section of this chapter is, of course, obviously, introduction to differential equations. Differential equation is a huge topic from all points of view. It's really a huge topic because differential equations are the basis of the models. And now, in the last year, everybody heard about models, mathematical models of natural phenomena. So, differential equation, let me write also O differential equation, where O is ordinary. The ODEs are the basis of the mathematical description of the real world. Okay, this is a very strong statement, but it is at least historically true. And I want you to really think of that and understand that. So when studying differential equations, we are not really concerned with a theoretical structure, but rather on the construction of models that have to be faithful to the reality. This is part of the truth. Okay, if you talk to a pure mathematician that studies differential equation from the abstract point of view, he or she will tell you that this is not true, that differential equations bear a lot of new mathematics and new theory. And this is true. But for us, you are becoming engineers, and I come from mathematical physics. So, and also historically, differential equations are really a powerful tool to link mathematics and reality. And this is a philosophically deep topics in the sense that the question why mathematics is so close to reality, why is it so useful to describe reality, is mysterious. There is no shared answer to this question in philosophy and epistemology and so on and so on. But however, what you saw last year with the number of new infection of COVID-19 arising, following exactly an exponential law, how predicted by mathematical models. And not only that, you see the curve having an inflection point and then go down. This was exactly what mathematical models had foreseen. And mathematical models, this sort of mathematical models, were basically differential equations. Okay, so it is really a huge topic, and I want to tell you that here in this few hours we will see really very few of this huge topic. Okay, we will see very few. And what we will see are three types of differential equation. The first is called the differential equation with separate variables. So the first topics will be the separation of variables. Second will be the first order and linear differential equation, ordinary differential equation. And third, the second order linear ODE with constant coefficients. Okay? I know that the words that I use here, separation of variables, also first order, linear, and so on are mysterious to you up to now. But I just wanted to say that we will bound ourselves to these three categories and lacking a bit an overall overview of these topics. And in order to have this overview, so in order to gain a general overview, of these topics, I can just suggest you some reading. The first is a really classic of the literature on models and differential equation, and this is called Ordinary Differential Equations by Vladimir Igorevich Arnold. Who was a Soviet scientist, a great mathematician, who spent the last years of his life in Paris, and he was professor in Paris in the end. And he is really a big name in the field of differential equations, model mathematical physics, and so on. The second is another big name, and it is a very different book. Probably easier, more popular. Also, the book by Arnold is not so difficult, but the second one has been written in a very special way in order to be read by not only mathematicians or physicists, but also by engineers, by biologists, and so on. So people having background in mathematics which is not so strong. And this book is entitled Nonlinear Dynamics and Chaos. And the author is Stephen Strogatz. He received many prizes for the best book in mathematics and so on and so on. This is really a wonderful book. And it is also full of exercises, and it touches many topics like chaos and also meteorology, which is of course linked to chaos, but also fractals and many other fashionable arguments, and every argument is very well and very clearly explained. Okay, so, and I want to start our lectures on differential equation not going immediately to the technical part, but I will try to give you a sort of overview of an overview, so a sort of a general sightseeing about the differential equation. Even though it is very difficult, I would need an entire course on differential equation in order to give you the real flavor of this topic. So this is a very rich and very nice topic. I like it so much. So let us start by an example. Probably the simplest example one can think of is given by the dynamics of population. So what does dynamics mean? So the word dynamics means that something is changing. Something is evolving as time passes. So a good and probably clearer synonymous for dynamics is the time evolution, the evolution in time. Evolution of what? In this case, this is the evolution of the population. So this is the quantity that evolves, where evolution just means change. This is the quantity that evolves in the sense that changes in time. So we are studying the population of, of a country, of a town, but also of bacteria in some laboratory, in some experiment. So there is a basic quantity that we want to model, which is the n of t, which is a function, of course, and this function denotes the population at time t. Okay? So when an amount of time delta t passes, we have the population n of t plus delta t. Delta t is supposed to be positive, for instance. Okay? And now we want to evaluate what is the change in population during this interval of time. So, the change of population in the interval of time between times t and t plus delta t amounts to, this is the change of population we are interested in, so it is n of t plus delta t minus n of t. Okay, this is the change of population. Now, think of the system you have in mind. So, like, this can be a biological system or a town and so on. So, this variation of population is due to the fact that there are people who die. So, there is a d t plus delta t, and with a minus sign because it is a negative change of population. So these are dead people in the time interval of interest. Oh, sorry, here notation can be made a bit more precise. So here you have d from t to t plus delta t. And then there are new people, newborns. So let me denote them by b, t plus delta t. And these are people born in the same time interval. And then there are people who came from abroad, so the immigrants plus I, the immigrants. So these are people that are arrived in our system, in our town, in our country, from abroad, from outside. These are the immigrants. And then there are here people who left the country in the same interval of time, so it is a negative change. So these are people who left the country. These are emigrants. Okay? Up to now we did not tell anything about the specificity of the system. This is extremely general. Basically, there's no information, just reasoning and gathering what we know. But now we start with hypothesis on our specific system. So first, we suppose that our system, country, town, or laboratory where we are cultivating bacteria or various viruses is closed. So there is no immigration, no immigration. So the system is closed. Which means that I, from t up to t plus delta t, is equal to E t plus delta t, which is equal to 0. This is the first hypothesis, so we can cancel these two contributions and our relationship is just here. Then, so this is the first hypothesis. Now we go to the second hypothesis. And this is a bit less intuitive, but we say that if delta t is taken to be small, then the number of deaths in the time interval, as well as the number of births in the same time interval, is proportional to the time interval. I would say small, but not too small. Because if it is too small, these numbers fluctuate. You can see easily from the statistics of COVID-19. What am I saying here? So I'm saying that, okay, first think if reasons why this is reasonable. If delta t is too large, then the outside conditions may vary. So if you consider the population of the world in the last 1,000 years, conditions varied a lot. So now we are cleaner, we have a more developed medicine, and so we have vaccinations and so on and so on. So now, this rate of mortality is much lower than before. On the other hand, there are less births because families are not so large like once and so on. So if you take a very large time, outside conditions that determine deaths and births are changing a lot. Okay? On the other hand, if delta t is too small, then statistic fluctuations may become very important. So if you see the number of deaths of birth every second or every single day, then you will find that it is not uniform at all. Okay, so the idea is that there is a sort of intermediate time scale So there exists an intermediate time scale that makes realizes this, let us call it asterisk, that realizes asterisk. Okay? And so when you realize asterisk, you can say the following things. Sorry, 1 minute. You can say that the number of deaths in this time interval is proportional to a coefficient, let me call it delta, and let me write it in red, n of t, delta t, and the number of births is proportional to the time, of course, to the number of people that are there, and to another coefficient beta. Or let me be a bit more specific here. So I told you that these numbers, death and births, are proportional to the time in our time scale. And yes, this is true. But of course, it must be proportional also to the population, because if you consider a small population, you will have less deaths and less births. So the coefficient of proportionality to the time depends on the population, the present population, and then there are some coefficients. Okay? So delta is called the mortality, beta is called the natality. They are rates. And now let us go to the starting equation, which is this one. So we have that n of t plus delta t minus n of t is equal to minus delta n of t delta t plus beta n of t delta t. So we can rewrite it as beta minus delta n of t delta t. And this is equal to alpha. We introduce this new parameter, alpha, n of t, delta t, where we introduced alpha that equals beta minus delta, and this is called the growth rate. Now, we can divide by delta t, and we get n, t plus delta t, minus n of t, divided by delta t, equals alpha n of t. So notice that this is the incremental ratio of n of t in the interval between t and t plus delta t. Now we can approximate the incremental relation with the derivative we get finally n prime of t is equal to alpha n of t. This is a strange expression. This is a strange expression because so we have an unknown, this is very important, unknown function n of t that is linked in a rigid, in a specific way, in this case very simple, that is linked to its derivative. So, the expression 2 asterisks this is an identity, of course, but with an unknown. So it is an equation. And since notice that first, the unknown is not a number, is not a variable x, but is a function. So it is a functional equation, but there is also the derivative of the unknown. Appears in the expression, in the identity. So, when these two features are present in an equality, we say that two asterisks is a differential equation. Moreover, since only the first derivative, not the second, not the third, only the first derivative only appears in the differential equation, one says that the differential equation is first order. And of course, we can also say that since the unknown appears there only linearly, which means only power 1, m prime and n. So no n square, no exponential to n prime, and so on and so on. This equation is called linear, okay? I will define rigorously all these terms, but just to give you the first words, the first hints, okay? This is a differential equation, an ordinary differential equation. This is the unknown. This is linear, and it is first order because there is only the first derivative, okay? This is called, so the equation double asterisk is called many ways, but one way is Malthus equation because it is an equation for the dynamics of population, and at the end of the 18th century, the priest Malthus wrote that we were growing too fast, so very soon the food would finish and then we all die. But at the end we are alive, and Malthus died, so there was something wrong in his way to use this model. Okay, of course, he did not write a differential equation. He didn't know mathematics at this point, but it is very interesting the way his reasoning is really describing what a differential equation does. And so we will see what are the solutions. And nowadays, Malthus' model is considered the first one in the study, the first model in the study of dynamics of population. Of course, these are only words. There is really no math. Also here in these passages, there is no math. We were constructing a model, okay? And constructing a model, we made hypotheses. It is not math. It are not theorems. We are not deducing anything. We are doing something else, building up models to describe the reality. Then we ended up for a model. We attached some words to this model: differential, first order, linear, and so on and so on. We were very happy, but we want to solve it. But we want to find a solution. But what is the solution? Which function satisfies? So I tell you what is a solution, namely, what function or what functions, plural, I don't know, really satisfy the equality n prime of t is equal to alpha n of t. Okay, you will see it in the next video. Stay tuned.